This is a cram session or a study session for the Google Cloud Associate Cloud Engineer exam. It's updated for the 2026 version of the exam, and I don't know exactly how long this will take, probably about an hour, maybe more, we will see. But I'm going to fly through the most important things to know for the exam. This will get you very far in covering what you need to know for the exam. It's not going to cover 100% of everything that you need to know, all of the little details that you need to know for the exam. That would take way longer. And if you want that, you can go to my website, gcpstudyhub.com, to get that. But this will be a free study session to cover a lot of what you need to know for the exam. So if this is your last day to study, if you're cramming, if you're scrambling to prepare, if you want to just review the important things, this will get you very far. So I'm going to go through the most important topics. I have about 70 slides or so to go through, and I'm just going to talk through the topics and show some bullet points and visuals on the slides, on the screen, and you'll be in good shape if you have the exam coming up. So let's get started. All right. So first, we're going to talk about the resource hierarchy in Google Cloud. And essentially, it's like this. At the top of the resource hierarchy, you have the organization, okay? Underneath the organization, you have folders. And then within folders, you have projects. And folders can be nested within each other as well. So if you've ever used Google Cloud, you know that the default resource for you to be using is the project, right? And projects don't need to be in folders, and they don't need to be in organizations. But a lot of the times what happens when you use projects in a company, in an organization, in the real world, is you do have multiple projects for different teams, or different things that you're building, different departments. And so you put these in a structure that represents the structure of your organization, basically. And so Google wants you to know that in GCP, you can organize your projects in this way. You can use a combination of folders and projects to organize your resources, and these would all be under the umbrella of a quote-unquote GCP organization, which you establish. Just essentially, you establish a domain, So like for gcpstudyhub.com, that would be my organization. That would be my domain. And I'd have multiple projects. I do have multiple projects and folders in my Google Cloud organization. So that is the resource hierarchy. You need to know that for the exam. Moving on. Project name versus project ID versus project number. So these are different ways to identify projects in Google Cloud. So you've got the project name, which is human readable. It can be edited at any time. It does not have to be unique. It's just like the display name of the project in console, for example. It can be something like analytics project if you are an analytics team or if you're using the project for analytics. And then we've got the project ID, which is globally unique. It is alphanumeric. It is immutable, meaning it cannot change. And it is what you usually use with gcloud commands and APIs. So for example, the gcloud command, gcloud config set project ID is an example of when you would use this project ID. So if our project is analytics project and we set it as analytics project in the beginning as like the project name, what Google might do is it might take that and it might, make a project ID or suggest a project ID for us, something along the lines of analytics-project- some kind of, number. Or if this is our production project, we might do analytics project prod, and then some number. We can set this ourselves, but it has to be globally unique. So if another project has the same ID as the one that we try to select or set, then Google will tell us we can't do that. But we do have the choice to try to set it to be something that we will remember or is representative of what we're going to be using the project for. And then we have the project number, which is globally unique. It is entirely numerical, and it cannot be chosen or modified. It is used internally by GCP. It's basically the thing that is used internally by GCP's APIs. But it's just good to know about because you'll see it, sometimes in like resource names in your Google Cloud project or, in APIs and things like that. So definitely know about that. Okay, you need to know about enabling APIs as well. So essentially, when you start a Google Cloud project, some GCP services are enabled by default and some are not. And you need to know for the exam that if you try to use a service and you get an error saying that the service has not been enabled, what you need to do is you need to go to the API under APIs and services, and you need to enable it. So this shows on the screen what it looks like for PubSub. But, really this could be for any service that you're trying to use in GCP that is not enabled already. One thing you need to know real quick, just a few bullet points, is you need to know about the migration of projects between organizations and how that is done. So projects, we talked about the resource hierarchy, right? Where you have organizations, folders, and projects within those folders. Projects can be moved across different organizations or folders within GCP, right? It doesn't have to stay where it is. And the migration, when that happens, is facilitated by a specific API method that is called projects.move. And gcloud and console, they use this API method under the hood, even if you're like clicking around or, using the console to do the migration. But you need sufficient permissions in order to perform this method, in order to perform this migration and call this API method. You need the resource manager.projects.update permission on the project that's being moved. And you need resource manager.projects.move on the destination parent. Okay, so this is a very specific thing that could show up on the exam. And you should also just know how projects can move between organizations. All right. How are we doing on time? Okay, we are at slide 6 and we're about 9-10 minutes in. Okay, cool. I'm trying to do about like a minute per slide, but I'm not going to rush through things that deserve a little bit more attention. Example roles at the organization level that you may need to know. Also, sorry, I'm a little sick, getting over a cold, so I may have to like clear my throat every now and then. Hopefully I won't cough or sneeze into the mic. If I do, I'll try to edit that out, but yeah, I am a little sick. All right, example roles at the org level. You need to know that at the organization level, someone can be given the organization administrator role, which gives them full access to all resources within the organization. They can be given the organization policy administrator role, which allows them to manage org policies, constraints, and conditions. They can be given the viewer role, which gives them view-only access to the organization. It's useful for audits and monitoring. And then there's the browser role, which is like kind of similar to the viewer role, but it's read-only access to the structure and the metadata of the projects and folders, right? So you even are able to view less data about the organization than if you had the viewer role. Now, one thing to note here is you notice organization policy administrator is different from organization administrator. Organization policies are essentially ways that you can enforce constraints on your GCP resources or conditions on your GCP resources so that, for example, compute engine VMs can only be created in the United States or in Germany, or they can't have external IP addresses, or only IAM principals with the domain name that matches your organization domain, can be added. Things like this. You can do allow lists or deny lists with these policies. You don't need to know the details of those, but know that they exist. And the role that someone would need in order to, at the organization level, administer those policies is the organization policy administrator role. Pretty self-explanatory. All right, moving on. Cloud IAM. So my brief and I think snappy and convenient definition of Cloud IAM is IAM, Identity and Access Management, lets you manage who, either a person or service account, has what access, meaning roles or permissions, to which resources in GCP, such as services. Now, IAM console lets you review all of the users, the service accounts, and their assigned roles. So you can do that in the console. You can do that from the gcloud command line tool. But typically I've seen it done in console unless you are like updating a lot of principles at once. And the role types that are available are basic roles, predefined roles, and custom roles. And I'll go over those a little bit more detail in a couple more slides. But first, let's talk about principals. So a principal, spelled PAL at the end, is an entity that can be granted access to GCP resources, right? So there are two categories of principals that you need to know. One is user accounts. So those are associated with a human. They are used for accessing cloud services. They are authenticated with a username and password, sometimes with two-factor authentication, like those codes that Google will send you when you try to sign in. And then there are service accounts, which are associated with an application or a virtual machine. They are used to enable automated or scheduled tasks, and they are authenticated through keys and tokens. And so you should know the difference between these, and especially the fact that service accounts exist, because I assume you're familiar with like user accounts as a thing. You use them all the time. But service accounts are meant for applications or services or VMs to be able to communicate with each other, right? So if you have an application, for example, that's trying to access BigQuery, you don't want to be signed in with your user account credentials on that application and using those credentials. You want a service account on that application to have access to the BigQuery data that it needs for the application to run properly. And so that's the idea behind a service account. Moving on. A little bit more detail about roles. So collections of permissions grouped together are called roles, right? So we saw, for example, the permission about moving a project. That was a very specific thing that a person can do. And that is what is called a permission. And when you group all of them together, when you group a bunch of them together, maybe in a related way, they are called roles, right? And there are three types of roles. There are the basic roles, predefined roles, and custom roles. Basic roles are broad permissions at the project level. Okay, arguably you would call actually organization roles that we went over earlier, basic roles as well. They are broad permissions, okay, encompassing many services. And then there are predefined roles, which are more specific. They are tailored for common use cases and job functions, and they're managed by Google. So there are things like BigQuery data editor, right? You didn't come up with that role. Google came up with that role. It is predefined by Google, and Google might even change the role over time. They have changed roles, especially in BigQuery, actually. If you've used BigQuery over the last like 5 or 10 years, the roles there have changed. So predefined roles are more specific. They are tailored for common use cases and job functions, but they are not the most secure role even. They're very convenient to use, and most people kind of stay in the predefined role approach. But custom roles, which are managed by you, they can be any combination of permissions. They allow you to get very, very granular and specific with permissions that you need for what you need to do. And you can grant, for example, members of your team very specific combinations of permissions that allow them to do exactly what they need to do. Now, doing that is kind of too much administrative work for a lot of teams and a lot of people. So often they will just stick to the predefined roles, and the jump from basic to predefined itself is already a big jump that is very secure in comparison to using the basic roles. But custom is there as an option if you want to use it. And there have been times where I've used it, or I've been on teams where we've used them. But I can't say I hear of them or see them being often used in practice. So let's talk about the risks of overprivileged access here. All right. Now you can imagine that when users, applications, or systems have more permissions than necessary, they can inadvertently or maliciously perform actions that compromise the security, integrity, or confidentiality of a system. For example, let's say we have a developer with unnecessary access to the production environment. They might accidentally deploy new code to the version of the app that users are accessing here. Or for example, an attacker who successfully hacks a low-level user account could exploit unnecessary permissions. So we're gonna go through exactly why you should care about overprivileged access and care about minimizing the risk of it and what the solution is. There's a principle that you need to know for the exam. So here we've got, an attacker who, let's say they hack a low-level user account. They've got read or write access as a result. And let's say that this user account that we gave read and write access to these services down at the bottom, they actually only needed access to BigQuery, Cloud SQL, and Dataflow. But we gave them access as well to Cloud Run, Cloud Storage, and App Engine. Now, because we gave this account overprivileged access, more access than it needed, the hacker here, who has unlocked the account and has gotten into the account, now has a wider sort of blast radius of his attack. The attacker can access not just the few services that the user was actually using, but he can also access these other services, right? Cloud Run, Cloud Storage, App Engine, that the account that he accessed, was not really using, did not really need access to. So we reduce the risk of a compromised account by avoiding overprivileged access, right? And then let's say we have a situation where, in addition to having more access than needed, one of the types of access that the compromised account had was access to Cloud IAM, which we just went over, is the way that you give access, permissions, and roles to accounts. So then imagine if a hacker got access to that account. Then the hacker could go into Cloud IAM and give himself basically access to anything, right? So privilege escalation is what we call that. That is something you also need to know for the exam. And it's something to be aware of as a thing to prevent or mitigate with the principle on the next slide, which is the principle of least privilege. So the principle of least privilege states as follows. This is my wording, but this is essentially the principle of least privilege. Always allocates the minimum necessary permissions for someone or a service account to do what it needs. Depending on your tolerance for role maintenance, usually this involves either custom roles or predefined roles. That's what you need to know for the exam, the principle of least privilege. And so you may be presented with scenarios on the exam where, an account is compromised and the attacker gives himself permissions to do even more things. And the question is, what does this violate? What common security consideration or principle does this violate? The principle of least privilege would be the answer. Or you might be asked what approach you should take to giving someone new access that they don't currently have, like a new team member or something like that. You should keep in mind the principle of least privilege. All right. Now let's talk about groups. So to manage multiple members of a team with similar or identical access needs, the best practice here is often to create a Google group, add each member to that group, and add the group to IAM with the appropriate roles. So typically this would be created with a Google Workspace domain. There are also Google groups that you can create without a domain. But it'd be created with a Google Workspace domain. And then a combination in the name, usually a combination of like the environment, the project or application, and the purpose or role, right? So like dev database readers at companyname.com, data scientists prod at companyname.com. That's just kind of a common practice. But you very well may see a question on the ACE exam testing your awareness and knowledge of the fact that groups, Google groups, are a best practice when you are managing multiple members with identical access needs. Let me pause this and get some water. All right, let's move on. You definitely need to know about cloud logging. You don't necessarily need to know many details about it, but you need to know that cloud logging is a service in GCP that enables you to store, search, analyze, and alert on log data and events from Google Cloud resources and applications. It used to be called Stackdriver logging. I'm adding that just for context. And it integrates with cloud monitoring for analytics and automated alerts. Speaking of cloud monitoring, so cloud monitoring allows you to collect, analyze, and visualize metrics from GCP resources. It allows you to monitor the health and performance of your applications and infrastructure. So you get these like dashboards, real-time metrics, and alerts. Along with cloud logging, again, they integrate together. It's part of the GCP Observability Suite. So there are some other services as well that are part of the Observability Suite. They allow you to have better observability into your services. But monitoring and logging are the two that you need to know for the exam. And again, it was formerly called Stackdriver Monitoring, but now it's been rebranded to Cloud Monitoring. And that's because I think GCP acquired Stackdriver Monitoring and Stackdriver Logging, which were products that some other company had built years ago. And then they fully integrated them into GCP and renamed them to Cloud Monitoring and Cloud Logging. So when you want to know what's going on with your services and applications, or you want to know, you want to dig into the details of the logs and figure out why something went wrong, Cloud Logging and Cloud Monitoring are what you should be using. So keep that in mind for questions on the exam. Now, this is one of my favorite slides in this presentation because I think this is one of the things that I wish someone explained to me right when I was starting to learn cloud. All right. And it's essentially this spectrum of abstraction, which arguably defines most, if not all, cloud services, and especially the compute services in cloud. And not just GCP, but cloud, other cloud platforms as well. But we're talking about GCP, so I've put the GCP services up on the screen. And we are going to go from left to right here. Essentially, as you can see on the slide, we have a range of compute services, and they vary in terms of the level of abstraction and operational overhead they require. So starting on the left with Compute Engine, okay, Compute Engine provides virtual machines or VMs. They give you complete control over your infrastructure. This is the service that you would use when you need the most flexibility and control over your compute resources. You need a bare metal machine. However, it also means greater operational overhead for you or your team since you are responsible for managing and maintaining the VMs, the operating systems, the networking configurations, for example. Sometimes you're responsible for updates. And so that's on one end of the spectrum, right? Now, taking one step to the right, we've got Kubernetes Engine. This is a bit more abstracted than Compute Engine. It leverages Kubernetes, which is an open source platform for managing containerized workloads and services. GKE is the shorthand for it. GKE is good for teams that are looking to orchestrate and scale their applications using containers. And so it does reduce a lot of the infrastructure management burden of Compute Engine. It still requires operational knowledge, especially of Kubernetes and of containers. Then we move to Cloud Run. Cloud Run is a fully managed compute platform that automatically scales your stateless containers. So it's really good for developers that are looking for a simple way to deploy their applications with minimal overhead, and you don't have to worry about managing the underlying infrastructure at all or scaling. It handles all of that for you. You just have to package up your container and deploy it. And I have Cloud Run and then App Engine, but some people could argue actually that App Engine would be less abstract and require more overhead than Cloud Run. Like Cloud Run has become just so convenient to use. But in App Engine, you don't even like package up the container yourself. GCP does that for you. You just fill out a YAML file basically. And so I kind of think of it as like requiring less of you to manage and deploy your application. But it kind of depends on your use case a bit. So yeah, so moving to the right, we've got App Engine. You know, it's a fully managed environment. And it actually requires fewer steps to deploy your application than Cloud Run. It's a platform as a service. It does handle things like capacity provisioning, load balancing, health checks. So if you want to just like focus on writing code and not worry about the app deployment and infrastructure management at all, like App Engine is a good choice. But I should say that it seems like Google is kind of deprecating App Engine. They're not really releasing new features with it. They're not talking about it in their like announcements and like marketing materials. There's a lot of people who think that like App Engine is just going to kind of like die, like fall by the wayside, because Cloud Run has just become so convenient to use. And then we've got Cloud Functions, and these are either called Cloud Functions or Cloud Run Functions. Google has not updated the name everywhere, although actually they are technically called Cloud Run Functions now. In exams, I'm still seeing them called Cloud Functions, so I put Cloud Functions on the slide. And Cloud Functions are a serverless compute service. They run your code in response to events. So like little like slices of compute, right? They're not entire applications. It's like code that can run in response to events, right? So they're very lightweight. They're very good for event-driven workloads, like processing files or responding to HTTP requests. And so the point here is that we move from left to right and we see a shift from greater overhead, more hands-on control, and less abstraction to less overhead, greater abstraction, and a fully managed serverless environment. I think actually for you, it's going to be on this side. On this side is Compute Engine, and over here is Cloud Functions. So greater overhead, less abstraction, and ops are required. Less overhead, greater abstraction, no ops, and serverless. And so the flexibility here allows you to choose the right compute service depending on your needs for control or your desire for things to be handled for you. And so GCP like intentionally offers this suite of compute services to cater to different needs of teams, right? And you will often see on the ACE exam and GCP exams in general, actually, language that hints at the right answer based on the level of overhead and abstraction that's required. So, for example, they might say, there's a company whose team is looking to migrate its applications to the cloud. They want, as little overhead and management as possible, or they want to use serverless services, or they want to use fully managed services. If they say that, that means they're not going to be using Compute Engine or Kubernetes Engine. They're probably going to be using Cloud Run or App Engine, right? So you can look for this language in the questions, and you can kind of tell what the right answer is as a result. All right, now let's get into a little bit more detail in Compute Engine. Compute Engine and Kubernetes Engine are probably the most tested on the exam, actually. So we're going to be spending a handful of slides on each in this cram session. So for Compute Engine is it's a scalable, high-performance virtual machine service running on GCP's infrastructure. Virtual machines are basically software-based simulations of physical computers, and they allow you to run an operating system and applications, if you so choose, in an isolated environment on top of a physical machine. Right. So we've got a little diagram here at the bottom. I just want to walk through it real quick. We've got the physical infrastructure at the bottom. This is the actual hardware that's like the CPUs, the disks, the RAM that make up Google servers in their data centers. These are the physical resources that VMs run on. So when you actually use a VM, it's not like there's like a dedicated like tower for you, right? It's actually that there's like all this physical infrastructure like spread throughout the data center. And then on top of that, we've got the hypervisor. It's a piece of software that sits on top of the physical infrastructure and manages all of that, right? And manages the VMs. So you can think of it as like a conductor, right? It's basically saying, okay, out of all this CPU and disk and RAM, this is a VM. And here, Ben from GCP Study Hub, you get this VM, right? So then from my perspective, it seems just like a VM, right? But really there's a lot more complicated stuff going on underneath. So the hypervisor makes sure that each VM is isolated from the others. And even though multiple VMs are running on the same physical infrastructure, they can't directly access each other's data or resources, right? The isolation is important, and that is handled by the hypervisor. And then we've got the VMs themselves on top. Each VM is a self-contained environment. It has its own operating system. That could be Linux, Windows, another operating system, its own applications. The VMs behave as if they are separate physical computers, and the customer using Google Cloud experiences them that way. All right, so I just want to make sure that you understand this because this could come up on the exam. And then we've got just a slew of settings for configuring your instances and managing them. So you have to select the region and zone for these instances. You have to select the machine type. There are a bunch of different machine types out there. Like the most common one, for example, is like N1 Standard 1 or N1 Standard 2 or E2 Micro. These are the cheap ones. But there are ones depending on how many virtual CPUs you need, or even if you need like GPUs, or how much memory you need. You know, you can pull up the list, and there's a VM for that use case, basically. And you can even customize them, actually. But you don't need to know that for the exam, or how to customize them for the exam. You select the operating system, the boot disk size, the network settings, you know, like network tags, whether or not you need an external IP address. Sometimes that is disabled by the org policy in your organization, as I mentioned earlier in the presentation. But you can reserve an external IP address if you need it. And you can also, you know, set firewall rules or apply firewall rules. And then also preemptibility. So preemptible machines are also known as spot machines, and they're basically machines that are cheaper, but they can be reclaimed by Google at any time. That is the trade-off. So they're much cheaper. I think they're like 50% cheaper in some cases. But Google can at any time say, hey, we actually need that VM for this other customer or something like that. And then you can't use it for some time. So that's what's meant by preemptibility. And so they're good for workloads that are cheap and can be interrupted. But if like you're using them for, you know, production workloads, that would be a bad thing, for example. There are other options as well for setting up, you know, compute engine machines, VMs, but these are the most important to know for the exam. All right, so now we've got managed instance groups. So I mentioned how Google Compute Engine is an unmanaged service. It is the least abstract requiring the most overhead. But sometimes you want a little bit of management with what you've got running on Compute Engine. And Google responded to this need by creating managed instance groups, right? It essentially simplifies the deployment and the management of VMs. It adds some management to this otherwise completely unmanaged service. So it does automated updates, it does scaling, consistency between them. It achieves high availability, load balancing, operations, or at least helps with these things. And so you kind of close the gap between Compute Engine and some of these other services or needs that might call for a little bit more abstraction. And one of the ways that this happens is with instance templates. So instance templates are essentially reusable blueprints to specify a machine type, an image, a disk, and managed instance groups, or MIGs, use these instance templates to create and manage fleets of identical VMs. So let's say we've got 3 different instance templates here. A MIG might take one, or you would specify one, to use for the MIG. And then we would have, here we have 5 VMs created from instance template B. So that's the idea behind instance templates. All right, autoscaling with MIGs. So autoscaling is typically not something that you would see with an unmanaged service, but with MIGs, we can autoscale. They can be set up with autoscaling. You specify the maximum and the minimum number of instances. Replicas, which are just instances in the instance group because the instances are the same as each other. So that's why they call them replicas. The default metric here that is used for autoscaling is CPU utilization. And by default, it is 60%, as shown on the right. But you can specify a different metric. You can specify custom metrics from cloud monitoring here. So you can do request latency or queue length, and you might have a question on the exam that requires you to use a different metric. All right. Let's talk about gradual deployments with MIGs here. So sometimes you want to minimize risk when updates need to be made to software or configuration on a MIG. What you want to do is you want to configure the max surge field, which is the maximum number of new instances that can be created beyond the current size. And you also need to pay attention to max unavailable, which is the number of instances that can be unavailable at any time during the update. So these basically define or constrain how new deployments can be done with your MIGs, right? So looking at the diagram here, we start with a managed instance group where all the instances are running version 1 of our application, right? And let's say we want to update with version 2. So the way this works here is the update process begins by creating one new instance with version 2, which has not joined our managed instance group yet. This is the surge instance, and this is added to the group without taking any of the version 1 instances offline yet, right? So once this new version 2 instance is healthy and running properly, this is the surge instance because we allowed max surge to be 1, right? So the process here continues where the new version 2 instance is healthy and running properly, and it replaces one of the old version 1 instances with another instance that is running version 2. And then the cycle repeats where we've got another VM version 2 that is spun up, and it is set to take the place of another instance running version 1. So this idea of a gradual deployment could be tested on the exam. Essentially, you don't want to all at once swap out your VMs because that could lead to issues. You want to gradually do it and one by one replace the VMs. So you add a new VM, with the new version that's a surge VM, which is constrained by max surge equal to 1, and then that replaces a VM that is running the old version, and then the cycle basically repeats until the entire MIG is replaced. So this gradual deployment strategy is something that could be tested on the exam. All right. Now, that's it on compute engine. Again, that's not like literally everything you need to know, but it is a lot of the important stuff. And now we're on to Kubernetes engine. So Kubernetes engine, or GKE, is a managed Kubernetes service that allows you to run, manage, and scale containerized applications using GCP infrastructure. So Kubernetes allows you to manage containers, and Google Kubernetes engine allows you to manage Kubernetes, basically, and use GCP infrastructure for it. So it simplifies things like scaling, updates, maintenance. It integrates with the rest of GCP. It's super convenient if your team wants to use Kubernetes. It is probably the most heavily tested GCP service on the exam. Like in terms of amount of detail that the exam is prone to going into, GKE is actually like probably the most tested on the ACE exam. When I say most tested, that doesn't mean that it's 50% or more of the questions, but it's more tested than other services, right? It might be like a handful, whereas the other services might be like 2 or 3. So make sure you know your GKE, and I'm going to cover a lot of what you need to know now. We need to cover a few core concepts here, the difference between a cluster, a node, and a pod. So a cluster in GKE, and actually just in Kubernetes, not just GKE, is a collection of nodes. The nodes are virtual machines, and they run containerized applications, which are managed by Kubernetes. So the cluster is the collection of the virtual machines. Virtual machines are what we use in compute engine. So you can see how, we're moving up the ladder of abstraction here. So a node is a worker machine within a cluster that can run multiple pods. And a pod is the smallest deployable unit in Kubernetes, which can contain one or more containers. So I've got the diagram here, which lays it all out. We've got cluster. The cluster can have multiple nodes. Each node can have multiple pods, and each pod can have multiple containers, one or more containers. All right. So I talked about preemptible nodes a second ago, but just to kind of make sure that you understand this, preemptible nodes are also called spot nodes. They are much cheaper than regular nodes, but they can be reclaimed by Google at any time. So this is the trade-off. If a pod is initially scheduled on a preemptible node that is later reclaimed, then the pod may be pending until they are rescheduled. So that sucks if your workload can't tolerate interruptions. So you need to make sure that it is good for batch, that it is used on batch jobs that can tolerate interruptions. Basically, any job that can tolerate interruptions, but batch jobs are usually the ones that can tolerate interruptions. So here we've got on the left, we've got a standard node and a preemptible node. The preemptible node is cheaper. Google suddenly reclaims it. The workload gets rescheduled to another node from the preemptible node, and there's no guarantee of when the preemptible node will return, so then there's a delay. Now for autoscaling in Kubernetes engine. So we've got 3 different types of autoscaler here. We've got cluster autoscaler, horizontal pod autoscaler, and vertical pod autoscaler. Cluster autoscaler scales the number of nodes in the cluster based on the overall resource demands of the pods. So we're literally talking about the VM instances that are in your cluster and adding or subtracting them, right? The best practice here is to constrain the autoscaler by setting a minimum and maximum number of nodes, because you don't want the autoscaler necessarily putting in an infinite number of nodes, and then you're paying for all that. But you also don't want it to undershoot the number of nodes. You might want to maintain a baseline. So that's a best practice that could be tested on the exam. And then we've got horizontal pod autoscaler, which scales the number of pods based on their usage, and it does not restart pods. It adds or removes pods instead. and it can scale based on either CPU, memory, or custom metrics. So again, quick little diagram down at the bottom. We've got our cluster in the blue, we've got our nodes in the pink, and then each node has one or more pods. And the horizontal pod autoscaler here has added a pod to each node. So we're talking about adding or moving pods. Vertical pod autoscaler scales the resources that are available to the pods, right? So the compute and the memory of the individual pods based on their usage. That is what gets scaled with vertical pod autoscaler. It may restart pods, and it cannot be done based on custom metrics. So just contrasting it with horizontal pod autoscaler. This is almost certainly going to be tested on the exam if you take the ACE exam. Okay, GKE Autopilot. So Autopilot allows you to automatically manage and optimize your infrastructure with GKE, right? It's a mode that GKE offers, and it automatically manages and optimizes the infrastructure for your clusters. The mode here is good for teams that want to focus primarily on the application layer without getting bogged down by managing the underlying infrastructure. So it's just adding even more abstraction to GKE, right? So it enforces some best practices by default, ensuring that your clusters are set up and run in a way that follows Google's recommended guidelines. Again, Google does not assume that you want this. You have to add it, but it is an option. It optimizes resource allocation and utilization, so that can help to minimize costs, although you're trusting that it would, do that in the way that you want. And it also handles maintenance tasks, basically. Node repairs, upgrades, security patches, without requiring your team to do it themselves or intervene. So it allows you to maintain your GKE environment with less operational overhead, letting you concentrate on developing and deploying your applications. Now let's talk about Kubernetes secrets. So in Kubernetes, secret objects can be used to store sensitive data, such as passwords, tokens, SSH keys. These are not limited to Kubernetes engine. They are actually a fundamental part of Kubernetes itself. So if you're using Kubernetes elsewhere, not just on Google, this is a thing. And let's just walk through this real quick. So first, a user would create a secret. This could be anything from a password to an API token or an SSH key. Your application might need this to access a service or something else. And then once the secret is created, it is securely stored within a Kubernetes pod. The pod acts as the execution environment for your containerized application, as we know. And so it keeps the secret safe from external access, basically. And then finally, the stored secret is used by the application to access a specific service. So this could be a database, it could be an external API, it could be another application. The secret is never exposed outside of the Kubernetes environment. It's there on the Kubernetes pod, maintaining its security throughout the process. So Kubernetes can help to provide a secure way to manage sensitive information is kind of the takeaway. And again, this could be tested on the exam. I've seen it tested on the exam. What's next? Deploying from Dockerfiles. All right, just going through this flow real quick. So Docker containers can be deployed to pods on your Kubernetes cluster. This is we've been beating this dead horse. Dockerfiles define what goes into a Docker container. And so the way that this works, all right, I mean, you do need to know this for the exam because Docker containers can be deployed, and knowing how to do this is actually like very important information for deploying application for Kubernetes clusters. So we've been talking a lot about containers in abstract terms, but how you do this with Docker containers and Dockerfiles is almost certain to show up on the exam. So a Dockerfile essentially defines everything that goes into a Docker container, right? You've got the operating system, the application code, the libraries, the dependencies, any other necessary files. It puts all of that into this container, or it defines what goes into the container, and that's why containers are so useful and transportable. And then what happens here is we create or acquire the Docker file that has the instructions needed to build your image. We use this Docker file to build the image. This is where all the defined components are packaged together. Once the image is built, it needs to be pushed to a registry. This used to be container registry, or either container registry or artifact registry. But now it is artifact registry. Artifact registry is the service that is used for this. And after pushing the image, you create a Kubernetes deployment manifest. This is a YAML file that references the location of the Docker image in the registry, and it contains instructions on how the container should be deployed. And essentially, the last step is you use the kubectl command line tool, all right, to reference the deployment manifest file and deploy the Docker container to your Kubernetes cluster. So that's why there's this line like going back as well, because the kubectl references the file that you created in step 4 and the image that you pushed to artifact registry in step 3. Okay. And so then it gets deployed to your Kubernetes cluster. So this sequence is super important for the exam. Now for Cloud Run. Okay. Cloud Run is a fully managed, no-ops serverless platform that is there to run stateless containers that are invocable via HTTP requests. It is very good for deploying things where you don't want to worry about infrastructure. So this could be microservices, this could be certain web apps, this could be APIs. So look out for those on the exam. And it eliminates the need for server management, allowing you to focus solely on your code. And again, it is for stateless containers that are invocable via HTTP requests. Now we need to talk about automatic scaling and kind of how this works in Cloud Run. So Cloud Run dynamically performs horizontal scaling. This is adding instances, not compute. We saw this with Kubernetes Engine, the different types of auto-scaling in Kubernetes Engine as well. Horizontal scaling is adding instances. Vertical scaling is adding compute. So Cloud Run dynamically performs horizontal scaling. And so instances are created or removed to handle incoming traffic. And an important aspect of Cloud Run is that it scales to 0. If there's no traffic, if no one is accessing your app that is deployed on Cloud Run or hitting your Cloud Run service with HTTP requests, it can scale down to 0 instances, which can significantly save on costs. This ensures that you only pay for what you use and nothing more. So, on the left here, we've got like normal traffic fluctuations with 2 instances. Let's say traffic increases, so then instances would be added, and then traffic goes to 0, and so does the Cloud Run service, right? So you only pay for what you use. Now, there is an important caveat to this, or trade-off here. For that next request that comes in after it scaled down to 0 instances, it can take Cloud Run, like a few seconds to start up, depending on your application. It can take it some time to start up in order to be able to respond to that request. So sometimes people try to like keep the service warm, right? And there's certain strategies for that too. But automatic scaling is definitely a big thing for Cloud Run. All right, introduction to App Engine. So App Engine, I mentioned this in the slide where we went over the spectrum of compute services. It's a fully managed platform as a service that allows developers to build, deploy, and scale applications without managing the underlying infrastructure. It supports several programming languages and frameworks. It essentially builds the container for you at a higher level of abstraction. So this is why I put it as a higher level of abstraction. You write your code like you write your application, and then you basically just fill out this form, this YAML file that tells App Engine, this is the kind of app I have. This is the programming language I'm using. And it will build the container for you. So you don't need to, you don't need to create the Dockerfile. You don't need to push it to artifact registry. You don't need to create the deployment manifest. App Engine requires fewer steps, but Google is increasingly just like pushing people to Cloud Run. All right, moving on to Cloud Functions. So Cloud Functions are, as we talked about in the Spectrum slide, the most abstracted and lightweight of GCP's compute services. It's a serverless execution environment, so obviously you do not need to manage any of the infrastructure. The code is event-driven, so it can be, triggered by different events in your GCP environment or HTTP requests. You've got automatic scaling with Cloud Functions, but there are limits on the execution time and on the memory and CPU that you can allocate to your little slice of compute that is under your Cloud Function. And it's basically, for those of you who are familiar with AWS, it's basically GCP's version of AWS Lambda. That's what a Cloud Function is. And again, on the exams, I'm still seeing them called Cloud Functions, but in a lot of the Google marketing materials and documentation, they're called Cloud Run Functions because they do use Cloud Run under the hood, essentially, and they have forever. But now Google is kind of being a little bit more transparent about that and integrating them kind of in the Cloud Run service in console and calling them Cloud Run Functions. But in exams and colloquially and just conversationally, people are still calling them Cloud Functions. All right, next one. Types of triggers for Cloud Functions. So they are event-driven, and this can be from a number of different sources. You can have changes in cloud storage. For example, when a new file is uploaded or an existing one is changed in cloud storage, this can automatically trigger a function to process or analyze that file. Or a new message in a pub/sub topic, for example. A Cloud Function can listen for messages published to the topic. This is useful in scenarios when you want to respond to new data or events across different parts of your architecture, like sending a notification or kicking off a workflow. And then you've also got just HTTP requests, any HTTP requests coming in. This makes Cloud Functions good for, building lightweight webhooks, APIs, microservices, where the function executes whenever a request is received. So this allows your applications that involve Cloud Functions to automatically respond to changes or events such as file uploads, message publications, as we've got here, or HTTP requests. It makes them very, I'm sorry. I'm getting over a cold. It makes them very responsive and allows you to build responsive applications. Okay, you get the point. Moving on. Now for Dataflow. So Dataflow is like bread and butter GCP. It is one of Google's services that they're most proud of. It does not feature prominently on the GCP exam. On the ACE exam specifically. But you need to know what it is. Like, it might show up, but it's probably not going to be like the key piece of a solution on an exam question. So Dataflow can handle both batch and streaming. It's Google's managed version of an open source tool called Apache Beam. The Apache ecosystem was basically built for big data needs. And Beam gets its name from a combination of batch and stream. So Google can handle both batch and streaming data. It's autoscaling, serverless. It integrates natively with cloud storage, pub/sub, BigQuery, and it has connectors for Bigtable and Apache Kafka. Pipelines must be located within a single region, so it's a regional resource. And it would offer, for example, a unified pipeline for fraud detection, handling both real-time and batch historical analysis. So fraud detection is an example I mentioned here because, it's with fraud detection, you occasionally want to analyze your historical data in a batch fashion, but you also need to handle the real-time analysis of whether or not the current activity is anomalous, right? So it's kind of a unique use case requiring both batch and streaming analysis, and like Dataflow is an example of where like that might be a little bit easier. All right, PubSub. So PubSub is a global scale messaging buffer, and it is Google's version of an open source tool, again, called Apache Kafka. It's no ops. It's serverless. Apache, again, is the collection of tools that were made open source and built for different big data needs, like in the first decade or two in the 2000s. Although tools are like being added to it still, the main ones were built or created at least like 10, 15, 20 years ago. It decouples senders and receivers, making systems more reliable as a result. So really this should be PubSub is a global scale messaging buffer or decoupler, not coupler. The idea here is that you have a sender and a receiver, and a sender can send a message, and the message can get stored in a PubSub topic, in a PubSub queue, and then there can be multiple receivers subscribing to that topic who would each get a copy, their own copy of the message. And so the receiver does not have to be ready to receive the message when the sender sends it. That's what's meant by decoupling. It is often used for data ingestion, like the first step in the data lifecycle in Google Cloud, although not always. But it's especially good for streaming data. And it can connect to other data pipeline services such as Dataflow. A common architecture is PubSub to Dataflow to like BigQuery or Bigtable or something like that. And it guarantees at least once delivery. It doesn't guarantee exact once delivery. You need to do something extra for that, but it guarantees at least once delivery. All right, so PubSub, not the most important service for the exam, but something that could show up. Okay. Now let's cover cloud storage, which is basically GCP's blob storage. It is GCP's version of AWS S3. For both, containers are called buckets. You've got individual files and items within buckets, which are called objects. It can accommodate all data transfer types, database transfer types, raw data, any format. Any kind of data can go in cloud storage. And it can control access to buckets, and you can control access to buckets and specific objects within the bucket, like your IAM policy can be applied to buckets, not just the service level, but the bucket level, and even specific objects within the bucket. So you can get very specific about it. It's got lower cost than most other storage types in GCP, and it is also something that comes with versioning and redundancy. So you can version your objects in cloud storage as well. And then you've also got different storage classes and regions or locations, which we can talk about as well. Actually, no, we won't talk about regions. We'll talk about storage classes. Regions is kind of self-explanatory. You can basically pick where your bucket goes. But so I should have mentioned this before we got into this slide, but we're starting to get into the data storage solutions here. Cloud storage is like the most basic data storage solution. Yeah, cloud storage is the most basic data storage solution because it can hold any kind of data, and so it's where a lot of unstructured data goes, like media files, text files, that kind of thing. But even database backups and archival data, because it's so cheap, goes into cloud storage a lot as well. So just know that for the exam. All right, so storage classes for cloud storage. We've got standard, nearline, cold line, and archive. There's no minimum storage duration for standard. There's a minimum of 30 days for nearline. There's a minimum of 90 days for cold line, and there's a minimum of 365 days for archive. What that means is if you store data in a nearline bucket, even if you take your data out at like day 15, you will have to pay for 30 days of storage. Same thing with cold line in 90 days, same thing with archive in 365 days. So you have to be mindful of what storage class you are paying for, what storage class you are selecting when you create a bucket. And the access patterns on the right here kind of tell you when you should choose each. Aside from just like cost considerations, you choose standard for high availability, low latency. For nearline, you choose it when you access the data less than once per month. For cold line, these are good for archives that still need to be available for disaster recovery, for example. And then the archive storage class is for like true long-term archives and backups, things that need to be accessed once per year or less, like for audit or compliance purposes. Like you really don't know if or when the data is going to be accessed ever, but you don't want to delete it. And storage classes can be set at the bucket level, but they can also later be set for specific objects. And one of the ways that you can change the storage class for a specific object is actually with Lifecycle Rules. And we're going to talk about Lifecycle Rules now. So Lifecycle Rules can be configured for objects within a bucket or even an entire bucket at a time. And they can be used to manage the transition of objects to different storage classes or their deletion based on specific conditions such as their age. So you set transition rules based on conditions such as the age of the data. It's good for deleting outdated or unnecessary data. It's good for cost reduction through automated management. And as an example, you can use the set storage class action, which allows you to change the storage class when a condition is met. You can change the storage class of an object in a cloud storage bucket when a condition is met. And that is something that I've seen show up in ACE questions. All right, common IAM roles to know about cloud storage. Storage admin is full control over cloud storage resources. Storage object admin requires you to manage objects in cloud storage buckets. Storage object creator, allows you to manage objects in cloud storage buckets, not requires you. Storage object creator, allows you to upload objects. Object viewer allows you to view or read objects. And then a legacy role, legacy bucket reader is it allows you to read access to bucket metadata and data. So cloud storage changed some of its roles. These are also I don't think these are all the roles available in cloud storage, but these are the ones that are most likely to show up on the exam if they do. All right. Now for cloud storage's role, potentially in data pipelines. So let's say we have an object that is uploaded to a storage bucket, okay? This could be any file, like a data set, an image, a log file, anything you want to store in cloud storage. As soon as the upload happens, what can happen in GCP is it can immediately trigger actions in other services, like PubSub, Cloud Functions, or Cloud Run, as shown on the screen. The upload can trigger a message to a topic in Cloud PubSub. And the object upload can also directly trigger a Cloud Function. And then with Cloud Run, you could even trigger an HTTP endpoint. So cloud storage and actions in cloud storage can actually serve as kind of the first step in a pipeline or a process in GCP that uses other services. Other available triggers here, other than like an object being created, include deletion of an object, metadata being updated, or the object being archived. All right, now for Cloud Spanner. So Cloud Spanner is a database. It's a relational database. It is designed for global availability, global scalability, and global consistency. Or like, not necessarily global, but covering a large geographic area, like multiple continents or an entire continent. If you see that on the exam and the question calls for a database solution, Spanner might be part of the solution. The claim to fame of Spanner is that it addresses the challenges posed by what's known as the CAP theorem, which states that it is impossible to simultaneously guarantee consistency, availability, and partition tolerance. It's actually limited by physics. And it's interesting to get into. We don't need to get into the technical details, but if you're interested, look it up. But that's why, global availability and global consistency and global scalability are like the thing that Spanner is known for. So it's pretty recognizable on GCP exam questions. Now let's go to Cloud SQL. So Cloud SQL is a cost-effective and fully managed relational database service on GCP. It's good if you're looking for a direct lift and shift solution for traditional MySQL or PostgreSQL workloads. The tech stack is managed for you. It manages backups, patches, so you don't have to worry about maintenance. It does also support SQL Server, but it has some limitations there, which we don't need to go into. Cloud SQL is particularly suitable for small to medium-sized data sets. I believe the limit on a Cloud SQL instance is like 64 terabytes of data. It's good for single region deployments, good for transactional use cases, OLTP processes. It's got strong consistency. It's ACID compliant, if you know what that is. Its queries are very fast, but it's not good for analytics. And if you're coming from MySQL, PostgreSQL, or SQL Server, Cloud SQL is a good option. So if that is something that is mentioned in a question on the exam, a team is coming from PostgreSQL or they're migrating their PostgreSQL or MySQL database, where should they put it? What should they do? Cloud SQL could be part of the solution. So look out for it. Let's cover read replicas now. So read replicas are copies of the primary or master database instance in Cloud SQL that help to distribute read operations so that the primary does not get overwhelmed. And it increases availability and scalability. So imagine here we have writes coming in from the application. Okay, we have writes and reads coming in from the application to the primary instance. What the primary instance can do to kind of ease the load, right? Ease the read load is basically replicate the changes that are being made in the primary instance to a read replica. And then the read replicas can also send reads to the application. So the Cloud SQL read replicas are confined to the same region as the master, in part because of how, close they need to be for there to be low latency between them, even though the replication is asynchronous. But it's important to note, that there is a slight delay potentially between the primary and the read replicas, right? So they're really good for scaling read-heavy workloads, but you should consider these limitations. This is something that could very easily show up on the exam. Google loves to test this. High availability and disaster recovery with Cloud SQL. So you can also configure failover replicas. They can be created to ensure high availability or disaster recovery. They should be set up in a different region from the master or a different zone within the same region. And essentially the way that this works is, let's say we've got the primary instance located in zone A. The application is communicating with the primary instance through reads and writes. We have a failover replica in zone B. Importantly, the replication between the primary and the failover is synchronous. That's important because it's literally a disaster recovery scenario that we want to be prepared for. And what that means is data is consistently replicated in real time. So there would be no loss of data during the switch if we did a switch, right? So if zone A, which is where the primary is, experiences an outage or any disaster that affects the primary instance, then the failover mechanism is triggered. And this allows the system, in this case the application, to seamlessly switch over to the failover replica and start using it that we already set up in Zone B. So that's why I've got like the tornado and the red X over primary instance in Zone A. Because suddenly we can't use it anymore. And so the application has to write and read with the failover replica in Zone B. So that's how you ensure high availability and a disaster recovery plan with Cloud SQL that could be tested on the exam. All right, we've got like 20 more slides. I'm hoping my voice holds up. Okay, Firestore, Cloud Firestore. So Firestore is a fully managed, scalable, flexible NoSQL database. It's offered by GCP. It's not like a version of an open source tool like some of the other ones that we looked at are. But you don't have to worry about the underlying infrastructure, allowing you to focus on building your applications. It's commonly used with here broadly defined, it's commonly used with varying loads, real-time updates, and high availability and low latency access to data. But if you have ever been part of a startup team or talked to one, like a lot of people especially in the early days of the mobile revolution, used Firebase and Firestore. And Firestore was like the database on Firebase. Firebase was like the mobile and web app sort of development platform that Google made available to teams. And Firestore was like the database on Firebase. And now it's kind of its own separate service. It's in Google Cloud Console without necessarily being part of Firebase. But that's useful to know because you can think of some of the things that it would be good for if it was used in those situations, right? So it's good for like user profiles. It's good often for like e-commerce data, right? It's good for a lot of situations where you need high availability, low latency, and lots of like updates to the data. It's not something that's going to be tested on the exam very much, and so we're just kind of cruising through though. Memorystore is a fully managed in-memory data store. It's useful as a caching layer. So this is a system that stores frequently accessed data in memory for better performance. So very, very quick, like sub-millisecond reads. And it supports two popular open source caching technologies, Redis or Memcached. So if you see those mentioned on the exam, you should think Memorystore, Cloud Memorystore. And a couple of examples of when it might be used are a news website caching frequently accessed articles, or a game leaderboard, with thousands of reads or writes per second because of constantly updating scores across like millions of users. Okay, Bigtable. So Bigtable is a fully managed, high-performance, massively scalable NoSQL database. It is one of those services that gets mentioned a lot as like one of Google's kind of claims to fame. It's designed for large analytical and operational workloads. Very rare for a database to be able to do both, but Bigtable is good at both. It's good for high throughput data that needs atomicity. So like, ACID compliance. There are other examples of NoSQL databases here that I want to mention. So there's Redis, MongoDB, Cassandra, HBase, Firestore, RavenDB. And so if you see a team, starting off with that and wanting to migrate to GCP, depending on the use case, they might want to go to Bigtable. Firestore, I should mention, which we just talked about a couple slides ago, is also a NoSQL database. So Bigtable and Firestore are the ones that like could show up on the ACE exam. And about HBase, I'm pretty sure Bigtable is the managed version of HBase. So in the theme of Apache software tools, like Kafka or Beam that we talked about, HBase, Apache HBase is the technology that spawned Bigtable or currently underpins Bigtable. And actually, I'm pretty sure Google invented HBase. So the way Apache worked was, you had these companies that were building these solutions for their various big data needs, and then they would get to a point where they would just open source it. And Google open sourced HBase, and it became HBase, and then Google created their own managed service of HBase, and that is Bigtable. All right, I hope that makes sense. It's not no ops though. You do have to configure the instances. So on the spectrum of, abstraction, you do have some configuration to do with Bigtable. It's not entirely serverless. Also, I need to correct myself real quick. I said it's good for high throughput data that needs ACID compliance. Bigtable is not fully ACID compliant. The A in ACID does stand for atomicity, but Bigtable enforces atomicity at the row level, but it's not fully ACID compliant. So I just wanted to correct myself there before moving on. All right, now BigQuery. So with BigQuery, you probably have heard of BigQuery if you've heard of anything on GCP at all. It is like probably the most famous, aside from maybe, I don't know, Vertex AI, although Vertex AI just got renamed as well. BigQuery is probably the most famous GCP service. It's a fully managed and serverless relational database. It's really good for both storage and analysis. It autoscales storage and compute. It accepts batch and streaming loads. It uses standard SQL or legacy SQL, but standard is what most people use. And it is basically GCP's data warehouse solution. It is GCP's flagship product. It's something they're super proud of. Some people actually move to GCP for BigQuery, or they incorporate BigQuery into a multi-cloud architecture or hybrid architecture involving on-prem databases and AWS databases and Azure data, or the rest of their architecture being in AWS or Azure. It is that good. And we're not going to get into all the details here. There's more that I go into in my professional data engineer course and in the database engineer course, which we are releasing in the next week or two. But BigQuery can show up on the ACE exam, and there are a couple of things that you need to know specifically about the way things are organized, and then like what you're charged for and what external tables are, among some other things, but those are the most important things that we're going to talk about today. So in the resource hierarchy in BigQuery, you've got the project level, which has one BigQuery instance. And then you've got within each project, multiple data sets, and within each data set, multiple tables, one or more tables. So just know that this is the hierarchy: project, data set, table. Okay? That just helps with sorting out what a lot of questions are actually saying. Because colloquially, we use data set and table like interchangeably. But a data set can contain multiple tables. It cannot, and the other way around does not work. A table cannot contain multiple data sets. Now, what do you charge for in BigQuery? You could have a cost question come up in BigQuery. So it's important to know that when you are performing queries, what you are charged for are the bytes read during query execution. You are also charged for data storage, but that is separate from running queries. So the way this works is your query is initiated, your query is executed, and then the bytes are read. The volume of your the volume of data that your query needs to access to generate the results is what you actually get charged for. And then BigQuery processes the data, crunches the data, performs any necessary transformations or calculations, and then you get the result, the output of your query. So it's that step 3, where the costs are incurred. Now, let's talk about external tables as well. External tables, we talked about cloud storage. External tables are when you have data in cloud storage that you query from BigQuery. All right? You run SQL queries directly on that data as if it was in BigQuery. So you might have a scenario on the exam where a team has data in cloud storage. They don't want to move it. They want, the fastest or most convenient way to query the data that's in cloud storage, but using BigQuery. This is the way that you would do it. You would set up an external table. All right, so that was data storage. Let's get into networking. Let's talk about what a VPC is and what cloud VPC is. So on the left, we have the characteristics of a physical network, and we're going to compare that to a virtual network. A physical network uses hardware components to facilitate communication and data transfer, right? We're talking about routers, switches, servers, cables. A virtual network abstracts these physical components into software-defined elements. So we're dealing with virtual firewalls. We're dealing with virtual network policies. We're dealing with segmentation, all right? Software-based segmentation. This is all managed through software. And at the bottom, we've got Cloud VPC, which is Google's virtualized network. So it's a logically isolated virtual network. It's essentially a physical network, but it is virtualized within GCP. So let's break down the resource hierarchy for VPCs in GCP. We've got GCP itself at the top. This is GCP's network. That's what that represents. Within GCP, you organize your resources into projects. They can be, obviously you can have folders and organizations, but VPCs are at least first defined in a project. Then you can share a VPC across projects, as we'll talk about in a second. So you have a project in GCP. Inside a project, you can create one or more VPCs. And as we discussed, a VPC is your logically isolated network within GCP, virtualized with software. And within VPCs, we have subnets. Our VPC spans two regions here. We've got US Central 1 and US East 1. Within each region, we've carved out subnets, subnet 1, subnet 2, and subnet 3. Subnets are further subdivisions of your VPC that allows you to segment your network and control traffic flow even more granularly. So in this example, we have two subnets. We've got subnet 1 and subnet 2 within the US Central 1 region. So you can have more than one subnet per region. We've got one subnet, subnet 3 in the US East 1 region. So you can see how this would allow you more flexibility to deploy resources across different geographical locations while maintaining your overarching VPC, while maintaining network isolation and control at different levels. At the VPC level, at the subnet level, depending on the location. Now let's talk about shared VPC. So this allows you to simplify network management across multiple projects. A shared VPC allows you to extend the network of one project to other projects within the same organization. This is what I was alluding to before. All right. So at the heart of our shared VPC setup is the host project that's in the middle. This is like the central hub. It houses the shared VPC network and its subnets like subnet A and B, which are illustrated here. And now we've got service projects around it. We've got service project A, we've got service project B, we've got service project C and D. And each of those have their own services, right? Cloud Run, Compute Engine, different databases, etc. These projects represent different teams or services, applications within your organization. You can imagine wanting them all to use the same VPC, right? So instead of each project building and maintaining its own isolated network, the shared VPC allows them to connect to the central network that is managed by the host project. So then the service projects can utilize the subnets within the shared VPC. They can more seamlessly communicate between various GCP services across projects. You have multiple departments sharing a common infrastructure. It's more secure, it's more simple. And so oftentimes organizations will kind of get to this point, right? So the benefits here are centralized network management, unified security policies, and more cost efficiency as well. It's just overall better once you get to a certain size, as long as there isn't kind of a contraindication. It's a really good way to streamline your network architecture in a big organization with multiple projects, multiple teams. I was in a team that did this. And this has a good chance of showing up on the exam. It's kind of like among the networking concepts in GCP, it's kind of like an intermediate concept, not an advanced concept, something that they would want you to know in the Associate Cloud Engineer exam, but it doesn't require a lot of like networking knowledge. It's pretty conceptually accessible. All right. Now for Firewall. So introduction to Cloud Firewall. Cloud Firewall is a service in GCP that allows you to manage a firewall, as the name suggests. It allows you to define and enforce control over network traffic to and from resources. It allows you to define and enforce rules that control network traffic to and from your GCP resources. It's mainly for virtual machines, but it also applies to load balancers, GKE clusters, Cloud SQL instances, potentially some other services, but those are the ones that are most likely to show up on the exam. And it includes both ingress and egress. Now, you need to know that you can create identity-based firewall rules, right? So, firewall rules traditionally are focused on IP addresses, protocols, and ports. Okay, that's usually how they're defined. But in the cloud, in GCP, you can define identity-based firewall rules, right? So when you associate service accounts with your instances and services, you can create firewall rules that explicitly allow or deny access based on those identities, those service accounts. And we know what a service account is because we talked about that in the beginning of the cram session. So this provides a more granular and flexible approach to security. It allows you to control access based on who or what is making the request rather than just, where it's coming from. And we've got a diagram here illustrating this. We've got Cloud Run with service account A. We've got a VM instance with service account B. And let's say we have a firewall rule that says deny the traffic if the source is service account B and the target is service account C. And if we look to the right, we've got another VM instance where the identity is service account C. The identity being run is service account C. So the traffic from Cloud Run with service account A gets to go through because there's no rule denying that. But the traffic from service account B on VM instance 1 gets denied because it matches the deny rule. So super convenient, and it could show up on the exam. Now, cloud load balancing. Cloud load balancing is a fully managed service that distributes traffic across multiple instances. It helps to ensure high availability for your application, scalability, generally optimized performance. It integrates easily with a lot of all of the main compute services. Actually, Cloud Functions is not mentioned here. I don't think it integrates with Cloud Functions. But we've got Compute Engine, Kubernetes Engine, Cloud Run, App Engine, as well as some other types. But again, those are the main ones that you need to know for the exam, especially Cloud Run. And I would say Compute Engine with a MIG or Kubernetes Engine. They're not really going to ask you about using a load balancer with like a unmanaged Compute Engine, but they're probably not going to ask you about using one with App Engine either. And just to show you kind of the way this works in practice, we have our clients on the left. These are the users, devices, applications trying to access your services. They could be web browsers, mobile apps, whatever. You being on your browser right now or your phone. And then on the right, we have the back end where our services are running, right? We see a couple of GKE pods. These represent containers running in Kubernetes engine or multiple containers. And then there's an App Engine service at the bottom too. So in the middle, we've got cloud load balancing, right? It acts as the director of the traffic that's coming from your clients. It distributes incoming requests from those clients to the available backend services. Now, how does it decide where to send each request? Well, it uses routing rules, and it can use health checks as well. So routing rules can be based on things like incoming IP addresses, the URL path, or even the content of the request. And then health checks are like pings that are constantly monitoring the availability and uptime of the backend services, right? Making sure that they're still up and running. And if a service becomes unhealthy, the load balancer stops sending it traffic, or it can redistribute the traffic, to other parts of the backend. So with cloud load balancing, you get that efficient distribution of traffic. So no single backend service gets overwhelmed. It stands in front of them and it routes those requests. Let's talk about Cloud IAP. We are nearing the end of our presentation, of our cram session. Cloud IAP. So Cloud IAP, it stands for Identity Aware Proxy, and it acts essentially as a gatekeeper for your web applications and VMs, ensuring that only authorized users can access your resources. How does it achieve this? It does this by verifying the identity of each user before granting them access. And it allows you to, another way of specifying through identity and access management, basically, in GCP console, which users can access your app. So it adds an extra layer of protection beyond just network security, firewalls. You focus on who the user is and what they're allowed to do, whether they are allowed to access the app. So with Cloud IAP, you can enforce granular access control policies based on the identity of the user, even for resources that don't have public IP addresses. That is what is very convenient about it. That's a specific scenario that could show up on the exam. So then you can still maintain a strong security posture while providing access to authorized users. And again, I've seen this being used. I've used this myself. It's a convenient service that probably doesn't get enough airtime in discussions of GCP, but it could show up on the ACE exam. Now, very briefly, how IAP works. Imagine we've got a user trying to access an application that we've deployed on Cloud Run. We've got the user on the left. We've got the Cloud Run service on the right. Normally, they would just send the request directly to the service, but with Cloud IAP protecting the Cloud Run service, IAP steps in as the security checkpoint, right? Intercepting that request before it reaches the Cloud Run service. IAP checks if the user has authenticated and is authorized to access the service. And if not authenticated, then the user is redirected to authenticate, essentially verify their identity with one of the methods above. And then the user's identity, if it checks out and they have the necessary permissions, gets granted access to the Cloud Run service. So IAP adds this layer of identity verification. And again, Cloud Run is not the only resource that IAP can protect. We've got App Engine. It can actually be put in front of a load balancer as well. It can also be put in front of a compute engine instance or application. So keep that in mind. But I do think Cloud Run is where it's most likely to show up on the exam. All right, now for Cloud Build. Okay, so Cloud Build is a fully managed serverless CI/CD platform. CI/CD stands for continuous integration, continuous delivery. You've probably heard of it. This means that you can automate the entire lifecycle of your applications from building and testing to deploying without having to worry about managing the underlying infrastructure. So essentially the idea here is that with Cloud Build, you can set up these automated pipelines that trigger builds, run tests on your code, deploy your code whenever changes are pushed to your version control system. It automates that allows you to automate that entire process, and also does it in a scalable way. And so it enables the philosophy of CI/CD, right? And you can specify custom build steps with containerized tools. That's important as well. You essentially supply this build script that defines each of the steps in the build pipeline. Now for Cloud Deployment Manager, which sounds like it would be similar, but is actually different. It is an infrastructure as code tool that allows you to define, deploy, and manage cloud resources through configuration files and templates. It's similar to Terraform. Both tools enable the infrastructure as code philosophy, which basically tries to take infrastructure and treat it like software and abstract it away. So you have these, configuration files, templates that you deploy, that you manage. And so it's easy to perform automated and repeatable deployments, right? Making infrastructure more manageable, just like we manage software. Configuration files for Cloud Deployment Manager. This is something I want to touch on. These are the files that allow you to define your infrastructure. They are in YAML, Jinja 2, or Python with Deployment Manager. You can either take a straightforward and declarative approach with YAML, or a more programmatic and dynamic approach with either Jinja or Python. And these templates allow you to scale and repeat deployments, right? So you can imagine like wanting to replicate your environment configuration in a GCP project in another project. Well, you could create a configuration file to do that, for example. So Cloud Deployment Manager is the managed infrastructure as code service on GCP. All right, getting to the last couple of slides. We need to touch on GCP Marketplace. GCP Marketplace is essentially an online store. It's accessible right from GCP console. It has ready to deploy solutions. You can think of like pre-configured software packages, virtual machine images, databases that are not offered out of the box on GCP. This is a screenshot of it. So you can see there's a lot of things that you can add to your GCP environment. But then, of course, you'd most likely be paying extra for it as well. But it does offer a convenient solution in some situations. So here's an example scenario on an ACE exam that you could come across, where GCP Marketplace, would be the solution. So imagine your team needs to deploy MongoDB Atlas. It's a managed database service to GCP. You need a quick and easy way to deploy and install the solution. What should you do? So the answer here would be to search for MongoDB Atlas in the Cloud Marketplace and then deploy it directly from the Cloud Marketplace, right? MongoDB Atlas is not a service that is already on GCP, so you would want to look for it there. Essentially, any question that you see where it's like you need a new instance of blank as fast as possible with minimal setup time, and you know that it's not a GCP service, the answer is often to get something from the marketplace. You typically deploy it straight from the marketplace without the command line or infrastructure as code. All right. So that's the end of the presentation. That's the end of the cram session. I'm coughing and my voice is at its hanging on its last thread. I hope that was helpful. This went longer than I expected, honestly, almost 2 hours, but I was happy to do it. I hope it was helpful. Feel free to let me know in the comments any questions, but this is a lot of what you'll need to know on exam day. So the full course for this is available in the description. or I'll pin it in one of the comments. It's at gcpstudyhub.com. And so if you want, all the details that you'll need to know for the exam and practice exams, I think I have like 5 or 6 practice exams up and available for people. This course still has a 100% pass rate. So if you want absolute guarantee that you will pass, go for the full course. And let me know if you have any questions along the way. Thanks so much. Take care.